Well, this video is for the first section of chapter 3, which is the last chapter in the textbook. And so this first section is about exponential, what are called exponential and logistic graphs. So let's talk a little bit about where they come from. So I often say that mathematics is about relationships because when we're talking about x and y graphing, we're talking about the relationship between x and y. And there are a number of different kinds of relationships. One is an additive relationship. You could have y equals x plus 5. And so y is always 5 more than x. And that gives you a graph that looks something like this. Okay. An example of that is the standard example I usually use is age. If someone is 5 years older than somebody else, they'll always be 5 years older. That will never change. The next kind of relationship we can talk about is a multiplicative relationship, where y is always equal to 2 times or some multiple of the x variable. And an example, this is the type of relationship that you see in proportional reasoning. Okay, if you're making any kind of mixture, anything that's a recipe, or if you're mixing chemicals together, then if you want more in the end, you've got to increase the amounts that you're mixing together. So that's a multiplicative relationship. Then we have what's called a polynomial relationship. Y equals x squared, and that is a curve, okay? So these two types of relationships are both what are called linear because they make straight lines because the x is to the first power. When we get x to the second power, then you start getting curves. And all of those powers of x are examples of what are called polynomial functions. Okay. What we're going to talk about is an exponential relationship. Okay? And this is where it's actually the variable that is in the exponent. Okay? So if we make a little chart for x and y values, let's see, I'll put some negative values in there as well. So if y is equal to 2 to the x power, when x is 0, y will be 1. When x is 1, y is 2. If x is 2, this will be 4. If x is 3, that will be 8. 2 to the negative 1 power is 1/2. 2 to the negative 2 power is 1/4. And that creates a graph. Here's the point 0, 1. And the graph looks something like this. Okay? All of these negative x values here will get progressively smaller fractions for their y values. And then if we keep going on in this direction, these will increase. They'll double every time, 16, 32, and so on. And that's why if you hear somebody talking about exponential growth, it's something that is growing very quickly. Now, in calculus class, we often talk about a rate of change. Now, as I'm erasing this, let's see, let's put up a linear function. Let's say y equals 3x minus 7. And you know that the slope is here. The slope is 3. And the fact that that slope is constant, let's see, there we go. The fact that that slope is constant is what makes this a straight line. So in calculus class, we do a lot of work with finding the slope of a curve at a particular point, right? You can see the slope here is very different from the slope over here, okay? And sort of the fundamental, really the defining feature of an exponential relationship is that the rate of change, or the slope of the curve, depends on the y value of the curve itself. Okay? That's often expressed as, we could say, dy dx is equal to k times the y value. Okay? And this dy dx is a way to write the slope. If you remember when you calculate a slope, I don't know if you've ever seen the delta y over delta x. And that stands for the change in y's over the change in x's, which is the slope. Okay? And so this relationship here is saying that the slope of this curve is going to depend on how big that y value is. Okay? Frequently, this is used in population mathematics that studies populations. So you would say dp dt is equal to k times p. And this idea that the bigger your population is, the greater your rate of change, the greater your rate of growth in population is going to be. It's what I call the more people, more babies relationship. Okay, the rate of change is proportional to the size of the population itself. And so that is what produces this exponential curve right here. Okay, so let's see here. Now, I've used the value of 2 as the base for our exponential relationship, where the x is up in the exponent there. Okay. Now, in most sciences and in mathematics as well, the base that is generally used is a number that we call e. So we'll call this y equals e to the x power, and e is on your calculator. I'll point it out in a minute. Let's see, it's 2.71828 ... Okay, this is a non-terminating, non-repeating decimal. It's an irrational number, similar to the way that pi is an irrational number as well. So, where does this number e come from? Well, I was talking a minute ago about calculus and how calculus is concerned with the slope of a curve. All right, so let's look at a couple examples of exponential relationships. All right, so they all pass through the point 0, 1. Because if you have y equals 2 to the x, then 2 to the 0 power is equal to 1. And if you have y equals 3 to the x, then 3 to the 0 power is also 1. So both of these curves are going to pass through this point. But the y equals 2 to the x function that I'm going to draw in blue is going to look something like this, whereas the y equals 3 to the x function is going to be doing something like this. Okay? And so they both pass through this point, but you can see that when the x's are negative, these y values are smaller, but when the x's are positive, these y values are bigger. Okay? So because of that, notice how when it's passing through this point 0, 1, the y equals 3 to the x curve is steeper than the y equals 2 to the x curve. Okay, if we draw these what are called tangent lines along there, you can see the slope as it's passing through there. This slope is steeper than this slope. And in fact, so what happened was the mathematicians were working with these relationships, and they wanted to know, well, what is the slope as it's passing through there? So let's take a look here. This is about 0.7 for the y equals 2 to the x power. And let's see, for the 3 to the x power, it's about 1.1. Let's see here. That slope is about 1.1. And they, examined what the slope is for some other numbers as well. And then they said, well, then maybe there should be a number between 2 and 3 so that when you make this graph right here, its slope as it's passing through this point is actually equal to exactly 1. Okay? So rather than making these graphs and calculating the slope, mathematicians made the slope equal to 1 and then back calculated what should this number be so that that slope is equal to 1. And the answer was e. Okay? So that's one place where e comes from in terms of calculus, is the slope of a curve. All right? And there are a variety of reasons in doing calculus why it's nice to have this number e as the base for our exponential relationship. And so we will be using that value. It's on the calculator. Let's see, let me point it out to you before we move on. There's two places where you can access E on the calculator. Let's see here. There we go. So one of them is over here, right above the divided by sign. You can see that E right there. Okay, so if you hit the second key and then divided by, that'll give you an E. So let's do that. And there's our E. And if we hit enter, then there's that value I put up on the board a minute ago, 2.71828, and so on. And that is a non-terminating decimal there. The other place where you can access E is down here. You see that ln key, and we'll talk about these in the next section, the log and ln. But there's e to the x power right there. So if you do second and then ln, you'll get e just with an exponent. Okay, and so if you want to know what e squared is, you can type in the 2 there and then hit enter, and so there it is. So there's two different ways to access the e. All right, and I'll talk about that more when we start looking at graphing these functions. All right, so there's a definition for E. Now let's talk about the application of these relationships. Now, the graph will use y equals e to the x. It looks something like this. Gets very large very quickly and just continues to grow exponentially. So people noticed that you could apply these ideas to things like population. And that differential equation I was talking about a few minutes ago, dp dt equals k times p. So here's the thing, is that once people started working with these ideas, this was kind of in the late 1700s, the early 1800s, people became very concerned that it looked like their population was going to grow very, very quickly and they weren't going to be able to feed people, which is sometimes a problem. Okay? So then in the 1830s, there was a French mathematician named Pierre Verhulst who looked at these ideas and said, well, okay, I can see the reason for this statement that the change in population would be proportional to the size of the population, but don't populations depend on resources? And shouldn't this rate of growth then be dependent on the state of those resources? That seemed like a reasonable thing to consider when you're trying to apply these pure mathematical ideas to an actual situation. So what Pierre Verhulst did was he took this equation and said, all right, I can see the reasoning for this rate of change being proportional to the size of the population. But what if we add in this other piece that says times 1 minus p over n? The n here is some theoretical carrying capacity, which has to do with resources. Okay? So this is the size, maximum size of population, or whatever it is in the application that we're concerned with. This is the maximum size of the population that can be supported by the existing resource base. And this is the population itself. So you can see that if this population is small compared to the carrying capacity, this is essentially just the original equation. Okay? Because this will just be 1 or something very close to 1. Now, as this p gets close to n, this fraction gets closer and closer to 1. So when we do 1 minus that, it makes it a very small number. Like if this is 9/10, then this will be 0.1. 1 minus 9/10 will be 1/10. And that'll make this rate of growth much smaller. Okay? So this is what's called the logistic equation. Okay? And we talk about this in calculus class as well. So this is the standard exponential relationship. The logistic relationship looks something like this. Let's see. It's basically y equals n over 1 plus be to the minus kt. So when we work with these equations, you'll get the equations in this format, and we'll mostly just work with graphs of them. We do some more with this in calculus class, but for our class, we're going to try to keep it pretty basic. Okay? So we'll look at some examples of logistic growth. The standard curve for a logistic growth curve looks something like this. And so we'll see this shape, this kind of lazy S shape, when we see some examples of logistic applications. And I can tell you that if you see some examples of the data from the COVID-19 pandemic, that the spread of the pandemic also follows something like a logistic curve. If I have some time, I'll put together something about the data and mathematics of the pandemic outbreak. But for right now, we're just going to focus on some of these more basic ideas. Okay, so that's the logistic curve. As a result, the pure exponential curve really doesn't have that much application, okay, for real life, because most things do not grow without any restrictions at all. Most things have some kind of restriction on their growth, and that's why the logistic curve is a much more realistic depiction of growth than the straight exponential is. Now, having said that, now if you take this y equals e to the x, you get a graph that looks like this. But if we take y equals e to the minus x, that kind of flips this around so that all these negative x's now is where that growth is. All the positive x's follow this curve that's coming down towards 0. Okay? And so I call this like a negative exponential. I sometimes call it the exponential tail. Okay? Now this does have applications. Okay? So let me talk about that a little bit, and then we'll look at some examples in the textbook. So this exponential tail or negative exponential, let's see, what are the applications for this? One is radioactive decay. Another one is Newton's law of cooling. And let's see, what's the third one? Oh, medicine in the bloodstream. So we've got examples of these 3 different kinds of applications in the textbook, and we'll see a few of them in a few minutes. The fundamental idea here is that these things are governed by the probability of things interacting with each other. So radioactive substances decay based on the interaction between the radioactive substance and the surrounding environment. Okay? And that produces a decay pattern very much like this. Newton's law of cooling is the same way. When something hot is placed in a cool environment, the interaction of the hot object and the environment surrounding it produces a cooling curve that looks like this. Let me draw a little bit better picture, and we'll see this on the calculator in a few minutes. But that's more a clearer picture of this kind of curve. And the same thing with medicine in the bloodstream. Okay, the medicine in the bloodstream is metabolized, and the rate at which it's metabolized depends on the interaction of the medicine with the metabolites in the bloodstream. And it's I heard Michael Pollan on the radio recently. He's a writer, if you've never heard of him, and he was said something about the half-life of coffee. And I was saying, what, half-life of coffee? Because half-life is something that people talk about in terms of radioactive substances. But coffee in your bloodstream gets metabolized in a very similar way. And so that's, when he talks about a half-life, that's the time it takes for half of the caffeine to be metabolized, and then it'll take the same period of time for another half to be metabolized, and so on. Okay? All right, let's see here. Let's look at some examples here. We'll start on page 145. So let's see what this looks like. So on page 145, we've got an example that is a negative exponential. This one is about medicine in the bloodstream. We've got a function here, and this is just in place of the y. Okay. And 150 e to the minus 0.12 t. Now when we type this in the calculator, we're going to use x in place of t. All right. So, part A says find the amount of medication in the bloodstream after 3 hours. So, at t equals 3, what's y going to be? And then in part B, it says how long will it take for the amount of medication to reach 60 micrograms. And so, we're going to say t, what's the t going to be when y is equal to 60? Okay, and let's see here. And the t is measured in hours, because that'll change depending on the problem. But in this one, the t happens to be measured in hours. So the first thing we want to do is graph this. And so let's see. Let's take a look at this on the calculator. All right. So let's get first off, let's get the camera to focus there. Okay. And then we hit the y equals key to come in here. Let's clear that out. Okay, so now we want to type in 150. So there's our 150. And then E, so I hit second, down here, ln. E to the, and then we use that negative sign down here. Right there, negative 0.12, and then the x is right there. So there it is. 150 e to the minus 0.12x, and then I'll hit the graph key, and let's see here. And we don't see anything, okay? So these graphs are not all going to be in the standard window. So one thing you can do is go into the table, hit second graph, look in the table. Oh, my table is a little non-standard here, so let me fix that. There we go. Now let's go back to the table, and now it's starting at 0 again. Okay, so now you can see when x is 0, y is 150, and it goes down from there. So we really have to play around with our windows here, okay? So the t is being measured in hours, so I'm going to hit that window key. The t is measured in hours, so we're going to take positive values. I'll make the x minimum 0. I'll keep the x maximum at 10. But down here for the y's, I want my y maximum to be 150, because that was what we saw in the table, right? In the table, you can see the maximum y value is 150, and then it goes down from there. So now if we go back to the window key, then that looks like a pretty good window to look at this graph in. So let's hit graph again, and there's our curve right there. Okay. All right, so now we've got an idea for how to put this on the calculator. So let's sketch this curve, and then we'll talk about how to answer these questions. So here's our window. This x goes from 0 out to 10. And the y goes from negative 10 up to 150. And then our curve is doing something like that. So we want to know the answer to the question, what is y when t equals 3? I can go right back into the table and just look and see what is y when x is equal to 3. Let's get the camera to focus on that. Come on. There it is. So when x is 3, y is 104.65. Okay. 104.65. Now there are a couple other ways that you can get that answer. So let me talk about that before we move on here. So again, let's get the camera to focus on this. Okay, so there's one way to see it is in the table. Another way to do it is if you hit second trace like we were in chapter 2, we were using choice number 2, find the 0. Choice number 1 is value. And so if you hit enter here, it'll bring you back to the curve and it says what x value do you want to know the y for? So we could type in x equals 3, hit enter, and there it is. When x is 3, y is 104.65. Okay, so there's another way to do the same thing. We can also quit, hit second mode, and that takes us out to the calculation window. And we can just calculate 150, right? So 150, and then e, so hit second, and there's e to the x. There we are. And then minus 0.12 times 3. Okay, so we've just input that 3 for the value of t, and when we hit enter, there it is, 104.65. So there's 3 different ways to answer that same question. Now, the easiest way, I think, is just to go look in the table, okay? But if that t value happens to not be a whole number, or if it's not in the table, like if they wanted to know something for 3.5 hours, then one of those other methods would be a good way to find the answer there. Okay. So that's part A. Part B says, what value of t will make y be 60? Now there are algebraic ways of solving this, right? What we would do is we would make the y be 60 and set up an equation that looks like this, and then we would want to solve for this t. And we will talk about how to do this algebraically over the course of chapter 3. But for right now, since we don't have those tools, what we're going to do is we're going to solve this graphically. We're going to put a line, we're going to graph a line where y is equal to 60. Let's see here. So that's 100, that's probably 50. So 60 looks to be about right here. Okay, so if we graph that line at y equals 60, then we can go and find the intersection point and find out what's the x value when y is equal to 60. So let's take a look at that on the graphing calculator. Okay, let's see here. Let's get this focused. Okay, so there's the calculator. So we're going to go back into the y equals and go down to y2 on the down arrow. So there it is. Just type in 60. There it is. Now go back and graph them both. And there's that line. Okay? Now, to find the intersection, we're going to go back to that calculate menu. Second trace. Second trace. So we talked about choice number 1, value, choice number 2, 0. See, choice number 5 is intersect. And so we're going to choose number 5. It's going to say first curve and second curve. We've only got 2 curves on here, so we can just hit enter. Yeah, that's the first curve. Second curve, yeah, that's the second curve. Guess, no, we don't want the guess. We want to know exactly what the intersection is. And there it is. Okay, there's the intersection. When y is 60, x is equal to about 7.6. All right, so that's how we're going to be solving those problems. And so we'll fill in the answer right here. T is approximately equal to 7.6 hours. Okay, so there's that first example on page 145. That's a negative exponential or an exponential tail application. Now let's take a look at another example. This is a logistic function. This one's on page 147. So let's see what this one looks like. Okay, so on page 147, so this is a deer population on a nature preserve. we've got y equals 8,000 over 1 plus 9e to the minus 0.2t. All right, so question A says how many deer were in the initial population? That's t equals 0. Part B says what is the deer population after 10 years? Let's see. Our t is in years, okay? So, after 10 years, we want to know what's y going to be. And part C, how long does it take for the population to reach 5,000? So you can see these questions are similar to the questions that we saw in that other example. Okay? But our graph is going to be a little bit different because this is a different equation. Okay. So let's go ahead and put that equation into the graphing calculator, and then we'll take a look and see what it looks like. All right, so first let's get the camera focused. There we go. So let's erase these from this previous example. And now we're going to go in and we're going to put in 8,000 divided by, and then we need parentheses. Okay, so divided by parentheses, 1 plus 9, and then we do that second e to the negative 0.2x. And then close off the parentheses, and we'll get something that looks like this. Okay, so let's go back to the standard window and see if we can see anything in the graph. No, okay, and I kind of knew that that was going to happen. So let's go into the table. Second graph will show us the table. And let's see here. Oh, I think it looks like I'm missing a 0 in my equation there. 8. Oh, okay. So that 8,000 is correct. But of course, when t equals 0, our value is actually 800. Okay, and then it's going to grow from there. You can see it goes from 800 to 3,000 pretty quickly, and that's true of these logistic functions. So let's see. So let's make our y maximum 5,000 and see what that looks like. Okay, so let's go down to the y maximum, put in 5,000. There it is, and let's see if we can see anything on the graph. Really, we're mostly interested in the positive values of x, so I think I'll change that. So now the problem is that we can't see anything over here. Okay, so I'm going to take out these negative values of x, and I'm going to push out the positive values of x. So let's make that x minimum equal to 0 now, and we'll make the x maximum equal to 20. Okay, so let's see what that graph looks like. And this kind of playing around with your window, I think, is helpful in these kinds of problems. Okay, so now it's growing past the 5,000 y that we had for a y maximum. So let's change the y maximum to 10,000. And let's see what that looks like. Okay. So you can see it's kind of got that lazy S shape. Okay. Let's see. Let's move our x maximum out to 30. And then I think we'll get a pretty good look at most of that curve. Yeah, and there is that lazy S shape. Okay, so that is a good look at this curve. And so I'll sketch this on the board with the window identified. So let's see, what are we working with here? So this is starting at 0. We put the x out to 30. We put the y up to 10,000, and then you've got a curve that kind of is doing that, okay? And this fast growth period right here, this is that period where it looks like it could be an exponential, okay? But then something happens that causes it to tail off a little bit. All right. And this is, so the thing about these logistic, so these are logistic equations, and the thing about these logistics is that it's kind of hard to tell what they're going to be doing. It could be doing this, it could be doing this, it could be doing this, okay? And this is what we saw with these applications to the COVID-19 pandemic, is that which one of these curves actually happens depends on how we react to the situation. Okay. All right. So here's the curve that we're working with at t equals 0. Oh, I think we saw that in the table a few minutes ago. Our y was equal to 800. At t equals 10, that's also in the table, and that's where y was about 3,607. And we're talking about deer population here. Okay, and then that last one, how long does it take for there to be 5,000 deer? And this one, again, we're going to solve this the same way we did in that other example. So let's take a look at this. Here's the table again. That's where I got the answers for parts A and B. For part C, we go back into y equals, arrow down to y2, and input 5,000. And so now that'll make a straight line where y equals 5,000, and there it is, okay? And now we want to know the intersection. So we go to the calculate menu, second trace, choice number 5, and then we hit enter to answer yes to first curve, second curve, and guess. And then we'll come out with the intersection. Y is 5,000, x is about 13.54 years. Okay. So in this case, t is about 13.54 years. Okay, so those are two good examples for this type of problem. Let's see here. What haven't we looked at yet? Let's look at problem 6 on page 151. So, problem 6 on 151. This is the Newton's law of cooling, or a temperature model. And so here our y values are 75 plus 95 e to the minus 0.12 t. And this says soup at a temperature of 170 degrees Fahrenheit is poured into a bowl in a room that maintains a constant temperature. The temperature of the soup decreases according to this model. What is the temperature of the soup after 2 minutes? So at t equals 2, what's our temperature going to be? And let's see, that's part A. In part B, a certain customer prefers his soup to be cooled to 110 degrees Fahrenheit. How long will this take? So if that's y, then what's the t value that corresponds to it? Okay, so again, we're going to enter this equation right here as our y value. Let's see here. So 75 plus 95 e to the minus 0.12x. And the problem tells us that the soup starts out at 170 degrees. And if you look in the table, you'll see that at t equals 0, y is 170. So that really is telling us that we want our y maximum to be 170 degrees. Okay? And let's see, the t that we're working with is in minutes. Okay, so this is in minutes. So let's look at 30 minutes worth of data and see what that graph looks like. Okay, so I'm going to go into the window, make the x maximum 30, make the y maximum 110, and let's see what that graph looks like. Okay, so that gives us a pretty good look here. Does something about like that. This line right here, instead of going to 0, that's going to be approaching 75. Okay, that's because of this 75 right here. And that's the room temperature. All right, so the thing's not going to cool off and become colder than the room around it. It's going to approach the room temperature of 75. So at T equals 2, the answer there is in the table. The temperature is 149.7 degrees. 149.7 degrees. And then when does it cool off to 110? So remember, this is the one where we have to graph that line. Y equals 110. There we go. And so we hit the Y equals key, go down to Y2, and just graph this horizontal line at Y equals 110 degrees. Go into the calculate menu, second trace, choice number 5, find the intersection, hit enter, and then there's our intersection, 8.3 minutes. Okay, so here's our answer. T equals approximately 8.3 minutes. All right, so that's it for this section 3.1. As always, if you have any questions, please let me know. This is the last section, well, this is the last chapter in the textbook. We're going to work our way through these sections, and like I said, if you have any questions, please let me know. Thanks.